I'm Rahman from Applied Research and Photonics. We are a research and development institute or company located in Harrisburg, Pennsylvania. And today, I will talk about layer-by-layer inspection of polymer quantum dots composites, quantum dots interactions by cameraless Terahertz imaging. So feel free to ask any questions you may have, but briefly I will go through some introductory notes and nanometrology, why terahertz, and a little bit about cameraless imaging. And then we'll go to the example, in this case is quantum dots in ionic polymer matrix, layer by layer inspection. So as a background, we are in the field of nanomaterials, and nanomaterials require, particularly their applications, require deeper understanding and their interactions with other materials, which is obvious from the scientific point of view, but there are critical knowledge gaps, and main challenges are measurement and standards for manufacturing, characterization of nanomaterials, interactions between nanomaterials and the bulk, characterization of the interfacial properties, and of course, the environmental health and safety issues. Now, many of these things are obvious, and often we wonder, having all the wonderful characterization technology today, why is there such a knowledge gap, and how do we, what do we do about that? So there are two things in metrology, which is measurement is the simple routine work of a single property, for example, and characterization requires detailed analysis. Therefore, it defines the key properties of certain materials. For advancing the usage in the industry, new unperturbed test methods needed, by which I mean that when we use techniques such as SEM or TEM and other techniques, there are a lot of sample preparation needed, which often perturbs the intrinsic states of materials. So, so that's what we mean unperturbed. And for large scale manufacturing, there is a need for replacing the expensive characterization methods with rapid, robust, and industrial scale techniques. So by nanometrology, of course, we mean the measurement of any nanoscale things such as nanomaterials, nanoparticles, of anything of the scale of nanometers and nanosecond, etc. And measurement is so important, or metrology is so important, because as you know, if you can't measure it, you can't manage it. As a phrase coined by Edward Deming, who popularized this field in manufacturing, Six Sigma and all of those things. Now, as far as scientific measurement is concerned, the challenge is lattice resolution imaging without electron microscope, or AFM or TEM, etc. And the challenge there is that the nanometrology for rescue of knowledge gaps includes interactions of nanomaterials with itself and others, nanomaterials at surfaces and interfaces, nanolayers, defects, delaminations, etc., semiconductors and nanomaterials, packaging, etc. So to give you some appreciation of this need, if we consider semiconductor manufacturing, which is not the main topic today, but just as an example. A blank semiconductor wafer cost only $100 or $200 in some cases. And when the fab process builds all the ICs on a single wafer, the value jumps of that wafer from $100 to $1 million or so, depending on the nature of the IC, size and number of them. So especially when the feature sizes are now going down to 10, even 5 nanometers, we need techniques and abilities to find and identify and manage defects that are on the order of nanometer or even smaller. Because if a wafer goes towards the end of the process and defect was not identified or cured, then tossing one single wafer cost $1 million. So this is a very important issue. Now for the problem today, I want to, I have spoken on the semiconductor stuff in the past at this forum. Today, I would like to focus on this quantum dot polymerized ionic liquid composite system. So because nanocomposites drive forefront research in nanoscience and nanotechnology-based product development, hierarchically structured emissive quantum dots of, let's say, cadmium sulfide or cadmium selenide, and with ionic polymer liquid composites, should exhibit solvent, responsive, ordered structural motifs. Analysis of the multi-length scale scattering is accomplished by using theory and modeling and small angle X-ray scattering measurement. So the time-dependent Ginzburg-Landau calculations verify the mesoscale cylinders arise from the topological constraints imposed by the in-plane perforations of the polymerized ionic liquid as it wraps around the hard spherical quantum dots. So consider the curtain on upper right corner. That is what is expected when this synthesis is done, meaning that this cadmium sulfide or cadmium selenide quantum dots in polymerized ionic liquid. We expect this cylindrical shaped structure around the quantum dots distribution. And this was confirmed from the small angle X-ray scattering, as we can see the spectrum on the top. So these results have been published recently in macromolecules. But before the publication, the biggest challenge was that, yes, we do see this thing should happen, but how can we actually see that structure? TEM or SEM gives only one single surface. So we don't know what's happening underneath the surface. TEM, when we polish to electron transparency, there are a lot of perturbation going on, meaning that the structures are not what you expect. And it's actually a general problem with TEM. Lately, we are recognizing that for more than one system. In case of ionic polymerized ionic liquid, this is a soft material. It's not very hard material. So it's not very easy to keep the structure and then put it in the TEM grid and be able to see what's happening not only on the surface and under the surface. So we took this project along with the Los Alamos National Laboratory and Argonne National Laboratory. Scientists from those two organizations and ours, we spent quite a bit of time to come up with the strategy And finally, we were able to produce the correct motifs and their images, which culminated in that paper. So terahertz multispectral reconstructive imaging, the fancy way of saying the cameraless imaging, that revealed that the subsurface structure along the cylinder axis undergoes dynamic rearrangement between two-dimensional hexagonal and cubic packing. And terahertz imaging was essential for confirming the predicted structure, because a lot of times seeing is believing, and of course quantification. One slide about our progress as a company. We started back in 2003 doing government projects such as SBIR and that kind of stuff, and eventually we came up with this high electro-optic coefficient material, and that turned into a Dendrimer Dipole Excitation mechanism for generation of high power continuous wave terahertz energy over a wide band range. And eventually we made we'll guide and guard the source. Then we made the first spectrometer, and slowly we were able to achieve less than 1 nanometer resolution in 2016. In 2018, we could see atomic lattice with the same instrument with a little modified version. So we are pretty happy about this ability to see the atomic lattice without using an electron microscope. The question is how we see that. So one thing is electron microscopes work for the atomic resolution imaging, because the electron wavelengths are in picometers. So we are able to see within the diffraction limit, or Abbe diffraction limit, we are able to see the lattice without the diffraction distortion. But when it comes to bigger wavelengths, such as terahertz, the advantage of terahertz is that it can penetrate through the material, not only on the surface, under the surface, we can see with it, but the difficulty is it's a huge wavelength, from few microns to few thousand millimeters, right? That's why it is also called millimeter wave or far IR. And I have a cartoon later to show where exactly it is. So Abbe diffraction limit, Ernest Abbe established in 1873 that the smallest object one can image cannot be smaller than half the wavelength of the light that is being used for imaging. So how do we overcome this fundamental physical limitation with millimeter wave, and we want to see atomic lattice, which is in angstroms or even sub-Angstroms? So then we came up with this stratagem. In the blue, as you can see, that the Beer-Lambert's law we rewrite in terms of the reflectance. We use a 3D nanoscanner for digitizing an object, and then use the three-dimensional lattice or matrix by computer algorithm to generate the image. And in doing so, then first we need the terahertz radiation, and this mechanism, as I mentioned, was called Dendrimer Dipole Excitation. And with that, here are some of the pictures how we came along. On the left, we had an opportunity to meet with Nobel laureates of 1996, known for their, father of nanotechnology or so, Harry Kroto and Robert F. Carl Jr. And then down the road, me and my mentor and collaborator, Donald Tamalia. So Dendrimer Dipole Excitation that we invented, eventually renamed as Rahman-Tamalia effect, which in a nutshell, the cartoon on the bottom, as you can see, we take this dendrimer, which is a nanomaterial, but it's a polymer and a spherical molecule. So it's soccer ball-like molecule, and there are smaller ones and there are bigger ones based on the generation. And when you dope this dendrimer with chromophore, that creates charge centers or dipoles. And the dipoles having a distribution, which I will explain in a second. And then we can excite those dipoles with a pump energy that gives out the terahertz. So this is basically, this is the RT effect or Rahman-Tamalia effect. And then with that, oh, here is the cartoon about that dendrimer, because when we dope it with chromophores, the charge centers are created, which is a function of the length scale. So not, unlike the inorganic lattice, where the dipole moment is fixed, in our case, we have a dipole moment distribution. And because of the dipole moment distribution, we get emission over a broader range. And that gives us a tremendous advantage for spectroscopy and imaging applications with this terahertz source. We get pretty high power, more than 200 milliwatt of continuous wave radiation, which, in pulse, it can go to even kilowatts. So the pulsing is not very favorable for materials. The purposes which are very similar to TEM or SEM, sample perturbation. Therefore, we stick to continuous wave radiation. Now, one other thing to say, how do we do the imaging with the cameraless technique, and how does it compare with the camera? So on the upper portion of the screen, as you can see, we have, in a camera, we have an object which is focused with the help of a focusing lens on a focal plane array, or commonly known as CCD, or it could be CMOS. And then that CMOS signal or CCD signal is converted into image. So in a sense, it's also a reconstructive image, except that it's on a focal plane, which is almost like a photographic film of the past decade. In case of cameraless, we have replaced that CCD and focusing arrangement by this nano scanner on the left, lower left. So the scanner scans an object and digitizes it in 3 dimensions, in all 3 dimensions chosen by the user. So what are the comparisons? In camera mechanism, image resolution is dependent on the CCD. Whatever the CCD gives, that is the image resolution we can get. And it's a strictly 2-dimensional image. In this case, in cameraless mechanism, image resolution chosen by the user is a non-contact versatile imaging technique. We can use semiconductors, nanomaterials, biological, any kind of material can be imaged. We get surface image, we get 3D or volume image, and we can see layer by layer image, which is what I will explain a little bit later. So it has the ability to replace other imaging modalities such as the SEM, TEM, and AFM. So for the sake of making a balance, we should also think about pros and cons. Is there any problem? So let me tell you the cons first. We have replaced the CCD with a nano scanner, but you still need that nano scanner. So because of that, it's not a real-time imaging. That's one of the biggest problem of this. There's not a real-time imaging. Once we scan, then we generate the image. And if we want to do the lattice resolution imaging, then the scanning takes a long time. And unlike the SEM and TEM, They can do elemental analysis. In this case, our object is not to do the elemental analysis, and it's not handheld like a camera. Although in scientific imaging, there are not too many handheld options anyway. But on the plus side, we don't need a CCD or a camera. Resolution is chosen by user. We can have small or angstrom resolution, or we can have macro resolution. And there is no sample preparation like TEM or SEM. And independent of sample size and shape, the sample size and shape has nothing to do with it. It can be liquid, solid, gaseous. Samples can be surface and subsurface imaging and layer by layer imaging. It can do the measurement of size and thickness from the image. So equivalent functionality as AFM, SEM, TEM, except for the elemental analysis. It's a tabletop system. This is how the system look like on the left side. As you can see, an optical table on which the main spectrometer and the gantry system where image is digitized, or the scanner, and a computer that controls all of these things. And the sample can be either vertical. For example, on the left, we have a gantry system where an wafer can stay vertically on the table, and the scanner will scan it. For smaller samples, we can also mount it right on the scanner in vertical fashion. And this is an algorithm that we use for converting the reflection matrix into the image. And the Beer-Lambert law on the right side, we have written the Beer-Lambert's law in terms of the reflected intensity as opposed to the concentration of solution, etc. And on the left, the traces, if we scan the same thing over and over again, the instrument must produce the same trace over and over again. So these are the conditions. And this general procedure, how we go about deciding what exactly need to be done. And here is a simple example that if I take a cosine function and want to make a 3D image, do I get a 3D image? And the answer is yes. Well, the algorithm works. Here is another example that we can actually measure the particle size. Once the imaging is done, a 3D volume image can be sliced into any number of layers, either on XY plane, YZ plane, or ZX plane. So we can inspect from any size and measure the particle size or layer thickness or the lattice parameter. So with that now, let me introduce this polymerized ionic liquid quantum dot composite system. As I said, this is a collaboration between Los Alamos, Argonne, and ourselves. So this TEM image we got from Los Alamos on the left, where you can see the quantum dots are embedded in the polymer. And their size from that TEM image, we get somewhere between, we get 11 nanometer or so. But it's predicted that because there is polydispersity, as you can see, not all quantum dots are the same size. So it's predicted that from 6 nanometer to 16 nanometer from TEM image, and we have done the terahertz imaging, we have found that is between 7 nanometer and 15 nanometer. So it's within the ballpark. In our case, on the upper right, as you can see, the pointer. So as you can see here, this is a plexiglass mount. There's a hole in there. On the hole, we have this polymer composite sample stabilized with tapes, and then this plexiglass was mounted on the scanner, and then the terahertz beam was focused on it and measured in reflection. So here, for example, here is one little particle here that's about 9 nanometer, but the range is between 7 and 15 nanometers. There are other quantum dots that came with aspect ratio, which we did characterize with full width at half maximum technique, which is very standard technique. And for different samples, we compared with TEM, but also because of the aspect ratio, if we take the horizontal diameter like this way, or if we measure vertically, then there is size difference which is expected for aspect ratio. Now, on the left, this is a three-dimensional image of 1 micron by 1 micron by 1 micron. But as you can see, the quantum dots are at the center, and the polymers made their cylindrical thing that goes from one end to the other end. And we can inspect them at every layer. You see this, this is not an animation on the right side. This is actually a video of the image from this top surface here, and we're going inward in this volume, and that's how the change on this surface, as you can see, happening. And in this case, the layer by layer inspection was done at every 2 nanometer. And then we focused on 500 nanometer by 500 by 500 nanometer volume. And then from this side, this surface, we're going again from one surface to another surface. And this is how the layer by layer at every nanometer, we can do the inspection this way. And then the next one is if you see on the left, a particular isosurface value gives that distribution, but then if we vary the isosurface value from one end to the other end and see the internal distribution of the polymer cylinders are changing, and the quantum dots remain in the middle, which is not shown here because the isosurface corresponds to a single value material, a single material corresponding to that value. So it shows clearly how the cylinders are arranged within the volume. This is 500 by 500 by 500 cubic nanometer volume. Within that, the isosurfaces are showing that the cylinders, the polymer cylinders, there are smaller ones, there are bigger ones, etc., concentric cylinders, but they are distributed. And you can rotate it, you can zoom it, you can inspect from all different kind of sides and angles. So this system can be completely characterized, not only to see their image, but we can quantify. We can see how they are interacting with each other. If you wanted to go to the structure factor and that kind of stuff, that can be done. Crystallography can be done. We can measure their lattice parameter, distribution, etc., which is what is published in this paper. Some of it, not all of it. More work is on the way. So with that, I think this is as much as I wanted to talk today, but there's other materials that we have studied and reported elsewhere. So I will skip that for now, and let me go to the conclusions. And if you have any questions, I'll be happy to try to answer. But what we have done is we have overcome the Abbe diffraction limit and imaged small items, or lattice imaging was done with the help of bigger wavelength in the order of millimeters. We also found that just overcoming the Abbe diffraction limit was not enough, because on the shorter end, for example, if you think that the wavelength is, let's say, 10 micron, then if I could image less than 5 micron, then I have overcome the Abbe diffraction limit. But that doesn't help me to get to the lattice imaging. So we came up with a stratagem where we have this modified Beer-Lambert's law, digitized an object, and used algorithm to convert the reflected intensity matrix into meaningful image. So this combination of a smart nanoscanning spectrometer and algorithm replaces the CCD for sub-nanometer resolution imaging. So you can think that it is in line of, someday in the past we had the photographic film. The film is nobody using today. That has been replaced by the CCD or CMOS sensor. Then the next step in line is, how about without CCD or CMOS sensor? And that's what we have done here, particularly for scientific imaging. I mean, obviously, if I wanted to scan a tree or something else outside, I could do that, but that is not very feasible, not practical. But for scientific imaging, if someone, you have experience with TEM, more than half the battle of TEM imaging is the sample preparation, rigorous polishing to electron transparency, and that perturbation of all kind, the high energy electron beam bombardment, etc., that changes material that lately people have been recognizing. Therefore, the unperturbed imaging without any sample preparation, not only on the surface but also below the surface in volume, layer by layer, has a real good merit. With that, I thank you for your attention and free to ask questions.
Thank you, Dr. Anis. It's a really nice presentation. If anyone have any questions, please proceed.
May I ask you a question about the technique? If you have a conducting sample, you are using electromagnetic radiation. What are the limits of your technique for conducting samples?
Very good question. So there are good things and bad things. Good thing is that you can measure the electron density, you can measure the electrical properties in reflection without touching them, etc., etc. And that's true for semiconductors as well, because that's one of the applications of this technique. Bad thing about metal is that the T-ray cannot penetrate into the metal, just like any other radiation. Metal reflects each and every radiation. So if we want to see, I had an example of nickel lattice imaging. We could penetrate about 2 micron or so inside nickel. But if I had steel or something else, probably it will be different. So if I have a semiconductor wafer, I can see 1 millimeter down the surface. If I'm imaging biological tissue, I can see 5 millimeter inside. But for metal, no, we cannot see that. So that's one of the limitation in this case. So what was the other question?
It was only this one question. Thank you very much.
Oh.